Alright, welcome back everybody. In this video we're going to handle examples 4 through 7 from the Substitution Part 2 lesson. We start here with example 4. We're integrating the integral of e to the 2t plus the secant of 2t tangent of 2t dt. Now something you should recognize notationally, which we haven't really seen up to this point, is whenever we have an integral, basically the integral sign operates like kind of like a left parenthesis grouping symbol, and the dt as a right parenthesis grouping symbol. So when we see this integral here, we really have implied parentheses around everything that's in between the integral symbol and the dt. Just a kind of a heads up for you here. Now I want to make a substitution here, and we've got the sum of two things, so I could opt to break this into two different integrals right off of the bat, but I'm not going to do that in this particular example because I'm going to make the same substitution for both of these. The substitution that I'm going to make for both of these is I'm just going to substitute u is equal to 2t, because then du is equal to 2 dt, and dt is equal to 1/2 du. And so, by making my replacement, I have 1/2 constant multiple I can bring out in front, times the integral of e to the u plus the secant of u tangent of u du. Alright, and now I can take this integral term by term. The integral of e to the u is e to the u. The integral of secant of u tangent of u is just secant of u. And then I can tack a c on the end. And so I end up with 1/2 e to the 2t plus 1/2 secant of 2t plus c. Or I could factor the 1/2 out. It doesn't matter. Alright. And there's my integral. Now I'm going to use a different tactic in example 2, because I have, again, two different terms, but I'm not going to make the same substitution into both of those terms. So I'm going to separate this integral right off the bat into the integral of e to the negative z dz plus integral of secant squared of z over 10 dz. And I'm going to make two different substitutions. For the first integral, I'm going to substitute u equals negative z. So then du is negative dz, and I can replace dz with a negative du. So this turns into negative integral of e to the u du. And for the second integral, I'm going to use a different letter. Instead of u, I'll use t, since t's on my mind from the previous example. So dt is equal to 1/10 dz. So 10 dt is going to be what replaces our single dz. And so making that substitution, we now have 10 times the integral of secant squared of t dt. And now I'm going to find both of those integrals by anti-differentiation. This turns into negative e to the u plus c plus 10 tangent of t plus c. And I combine those two c's into just a single constant of integration. And now I'm going to bring u back. And I'm going to bring t back. And there's the integral of that expression. So when we have the sum of multiple things, we can break them down into two separate integrals and use two different substitutions to find those integrals. Alright. Example 6 does not immediately look like one that we would handle using substitution, but we don't know anything off the top of our head that we can take the derivative of and get tangent of x dx. So in fact, this is going to turn into a substitution problem. We just need to replace the tangent of x with what it's equal to in terms of sines and cosines. And then we'll make a substitution. The substitution we will make if we run into a fraction like this is always going to be what's in the denominator. So we'll substitute u equals cosine of x, and then du is equal to negative sine of x dx. So sine of x dx is equal to negative du, and so I'm going to replace this sine of x dx with a negative du, and this turns into negative integral of du over u. Taking the integral, we now have the opposite of the natural log of the absolute value of u plus c, and bringing u back, we end up with the opposite of the natural log of the absolute value of the cosine of x plus c. And so that's something that, if we take the derivative of it, results in tangent. Okay? Alright, and our last example for this particular lesson, we're going to integrate 1 over x natural log of x dx. Now, a lot of times we would just substitute the entire denominator. If we substitute the entire denominator here, though, we find out very quickly that that's a bad choice. Let me show you what happens in that case, just so that you know how bad of a choice this turns out to be. If we tried to substitute u equals x natural log of x, then du would be equal to, and we need to apply the product rule to this, so we've got x times the derivative of the natural log plus the natural log times the derivative of x, all times dx. And if we tried to make that substitution, we would end up with this quantity as du. And I don't have this quantity 1 plus log of x anywhere in my original integrand, and so I would have very much difficulty replacing it in this fashion. We'd still have an x left over with a bunch of u's in our integrand, which we don't want. We want everything in terms of u. But you can make a better substitution here than the entire denominator. And if you know your derivative rules well, this is going to be a little bit easier for us. We should know that the derivative of the natural log of x is 1 over x dx. So in fact, if we look at what I've highlighted in yellow here, the derivative of that is entirely what comprises the rest of this expression. So if I do u equals the natural log of x, then du is 1 over x dx. And that is exactly everything else that's left from what I made, from where I made that substitution. And so by making this substitution, this turns into the integral of du over u. And that I can find the antiderivative of. It's natural log of the absolute value of u plus c. And so my integral of the original, bringing my u back, that's going to be the natural log of the absolute value of the natural log of x plus c. And that's something that if I take the derivative of it gives me 1 over x natural log of x dx. Alright, that's the end of this video and the end of this lesson. See you guys next time in Substitution Part 3, where we look at some truly tricky and more difficult substitution problems. Alright, see you then. Have a great rest of your day.